Welcome. In this video, I'll be talking about naive Bayes classification, specifically naive Bayesian machine learning, and even more specifically, we'll use an example of how to identify a disease with a naive Bayesian classifier. In other words, we'll try to answer the question, am I sick or am I not sick? Classification involves any sort of problem where we're trying to predict or identify a categorical outcome. Ordinarily, it's a binary outcome, a yes or a no. The example of spam, is this text spam or is it not spam? Identity theft, has this identity been stolen or is it not stolen? And disease identification, does this person have the disease or do they not have a disease? Let's focus on that example. There is a new disease spreading in Canada. It's called Board 25. It was discovered in spring of 2025, and we do have some tests for it. The current test is very expensive. It costs $5,000. It's very time-consuming. It takes 5 weeks to get results back, but it is definitive. In other words, if this test says you have this disease, you absolutely have this disease. And if this test says you do not have the disease, you absolutely don't have the disease. But can we develop a fast, low-cost alternative? Let's try. People have come up with a quick alternative to it. So to remind you, the old test was very expensive, $5,000. The new test, on the other hand, only costs $1. So orders of magnitude less expensive. The old test was very time-consuming. The new test, very fast. Can get an answer within 5 minutes. The old test was definitive, meaning it was 100% certain and accurate. The new test is 98% accurate. That seems like a pretty good trade-off. But really, is this test any good? You might be thinking 98% accuracy, that sounds great. But not quite so fast. Let's have a closer look at this. How do we evaluate a test overall? And what do we mean by 98% accurate? We're going to look at a confusion matrix, and confusion matrices are a very common way of identifying classifiers. They're algorithmically agnostic, meaning it does not matter what tool you used to classify something. It could have been a neural network. It could have been a linear discriminant analysis. It could have been flipping a coin. No matter how you made your classification, we are able to evaluate it using a confusion matrix. And a confusion matrix will typically look just something like this. We've looked at 200 people with our new test. 100 of them were sick and 100 of them were not sick. And then we applied our test to it. And we saw that it also assessed 100 people as being sick and 100 people as being not sick, but it wasn't perfect. So for example, among the sick people, there were 98 people that were sick, and the new test correctly identified them as being sick. There were 100 people who weren't sick, and 98 of those were correctly identified as being not sick with our new test. But you'll notice that there were 2 each of people who were sick but were identified as not sick, or not sick and identified as being sick. Nevertheless, it's a pretty good test. 98% of the time, we're making a correct identification. So if I test positive, I'm 98% likely to have Board 25, right? Well, maybe. It really depends on an idea of prevalence. And to help build some intuition on this, let's talk about Bayes' theorem. Or to put it another way, when 98% really isn't 98%. You may recall from basic probability, and this is a simplified version of Bayes' theorem, usually called Bayes' rule, and it deals with conditional probability. So the probability of X is the probability, of X happening, an event of some sort. Probability of X and Y is a probability of both events, X and Y, happening. That's not quite the joint probability function. but then there's the probability of x vertical bar y, or probability of x given y, and that is the conditional probability of x given that y has already happened. And so Bayes' rule can be applied this way. The probability of y given x is equal to the probability of x given y times the probability of y, all divided by the probability of x, where x and y are both independent events. Let's dig into that a little bit more. And you may have to pause here to think about that and reflect upon it. Perhaps I'll make a video at a future time going into a little more detail about Bayes' theorem. So consider our overall population. Suppose we've got a very small village. Total population is 5,000 people. In this population, we have 100 people who are sick and 4,900 who are not sick. And we give our test to all of them, everyone in town. We give the quick test to, which again is 98% accurate. So amongst the sick people, 98% will test positive. They'll be registered as being sick, but 2% of those sick people will say don't have the illness, or 2 of them. Similarly, amongst the 4,900 who are not sick, 98% of them, or 2% of them, will be tested positive. In other words, will be wrong. We'll incorrectly identify them as having a positive outcome. They'll be sick. Conversely, we'll be correct on 4,802 of them, where they'll be registered as negative, or 98% of that group. And we saw that from our previous chart. So if we were to apply Bayes' rule to this, we'd work it out, and we would see that the probability of being sick, given that you've tested positive, actually works out to being 50%. And this sort of makes sense. If you look at all the people who tested positive, in our example above, you see that there's 196 people who tested positive. 196 people who tested positive, but half of them have the sickness and half of them don't. So if you test positive, you're only 50% likely of being sick with this illness. So what on earth is going on with this Board 25 test? In other words, what happened to 98%? You're now telling me the test is only 50% accurate? Well, sort of. It depends on how many people are sick in your overall population. And this is why it's so important to know what the overall prevalence of a disease in a population is. If you don't know that, it's very, very difficult to have a lot of confidence in the individual tests or know how to properly evaluate them. Many times you may have gone to the doctor, and the doctor may ask you with an illness or a potential illness, and the doctor may ask you a number of questions beforehand. And you may think that they're just pre-screening, but that's not true. What they're actually doing is trying to help them identify the overall prevalence, the general likelihood that you might have an illness. In other words, they're trying to change the numerator on that previous slide. So in the case of Board 25, do you live alone? Yes or no? Do you have reliable internet? Yes or no? And are you under 20? Yes or no? So asking these sorts of questions not only help people figure out if a patient should have the test, but they also help determine how to better interpret the test once they get those results. How does that work? Well, what we see here is depending on people who answer yes or no to each one of these. So for example, if you don't have reliable internet, 90% of the people who say they don't have reliable internet are sick. They have Board 25. 96% of the people who answer that they do have reliable internet are not sick. Of the people who are sick, 85% say they live alone, And those who are not sick, 95%, say that they do not live alone. So if you live alone, it seems you're more likely to be ill, with bored 25. And similarly, if you're under the age of 20, and you are not sick, that represents a small proportion of people. In other words, amongst the non-sick people, only 7% are under the age of 20. 93% of the people who are under the age of 20 are not sick. Sorry, the other way around. 93% of the people who are not sick are under the age of 20. Similarly, amongst the sick people, 53% of the people who are sick are under the age of 20 and 47% are not. And then the final column just shows the overall prevalence of being sick or not sick. So 53% of people have reliable internet, 47 do not. 45% of people live alone, 55 do not. 30% of people are under the age of 20 and 70% are not. So if we put that into our overall equation, our overall Bayes rule, what we'll see is that a patient who has reliable internet, lives alone, and is under 20 years old, the probability that they're sick, given all of those things, is about 31, and the probability that they're not sick, given all of those things, is about 2%. But you may quickly notice there's a problem. Those probabilities don't add up to 1. You're either sick or you're not sick. The probability of being sick should be equal to, the probability of being sick plus the probability of not being sick should add up to 1. And in this case, it doesn't. So what's going on? We have correctly, sort of, applied Bayes' rule. But Bayes' rule, you may recall, is predicated on the presumption of independence. And this is why we call it naive Bayesian classification. It violates the assumption of independence in Bayes' theorem. So here's another way to describe this idea of independence. If you like peanut butter and you like tea, then a naive Bayesian classifier will calculate that you will probably like peanut butter tea. And we all know that, well, most tea drinkers would not like that at all. So really, we can come up with an approximation of the true probabilities by looking at the ratio between those. So back to our test. If we pre-screen and we look at that underlying prevalence or underlying likelihood based on those questions of having the test, and then apply the test, we'll see some very different results. So the probability of being sick, given that you've tested positive, again, here's Bayes' theorem again, and we multiply through this, and you'll notice that the underlying probability of being sick is now 93, based on our previous pre-screening questions. Working that all through, if you've done a pre-screen, our probability of being sick, given that you've tested positive, has jumped from 50% to 99.92%. So essentially, by pre-screening, we've moved from a 50% certainty to a 99.92% certainty. Now, it is true that we've assumed independence, so it may not have gone all the way up to 99.9, but we have absolutely moved it up from 50%. We are much more confident, if I can put it that way, that someone actually has the disease if they've tested positive than we were before. So why don't we just use this everywhere? Well, there are a few cautions that I need to present for a naive Bayesian classifier. It is fast and easy to predict different classes on a data set. And when that assumption holds, naive Bayesian classifiers are excellent. However, it is a bad estimator overall. We cannot rely upon those probabilities. And with highly dimensional data, it's very, very challenging. because a particular category may have nothing in it. I won't speak in this video about the curse of dimensionality. Perhaps I'll make another video at another time speaking about that. So the headline is very useful tool, very quick, useful classifier. Need to be very, very cautious about the probabilities, and most effective when you understand the relationships between the variables or the inputs that you're using and can determine the overall independence. Hopefully this has been helpful to you. If it has been, I'd invite you to click like and perhaps even subscribe. As always, if you do have suggestions or other things that you would like me to experiment with or explain, feel free to put those in the comments. I do read all those comments and do take those requests in mind. Thank you as always,